we're pretty much on schedule. I'll show you later the revised schedule for today. Yesterday. So, again, welcome to Pedro. This is the second talk on Riemannian hyperbolization.
So remember I mentioned yesterday that you take hyperbolic K space and warp it by hyperbolic F space with warp it with cosine hyperbolic R. Remember, it's the distance. It's the distance in Hn from x to some fixed point, some origin that we choose in HL. So think of this as being
Not in HN, HL.
yes, sorry. So think of the HL being here, so this is HL, you have a zero here or an origin, and then R is the distance to that point, and then you multiply this by HK, and these HKs get, they get multiplied, the metric gets multiplied by a constant depending on the distance to this point. So as you get farther and farther away from this point, these lines get kind of bigger and bigger. So in particular, if you have another HK here, so these distances, the point here corresponding to the same point, even HK coordinate, these distances get bigger and bigger. This kind of disciplines are like that. In the two-dimensional case, things go like that. And what I did was replace this HL by any metric that has a kind of an origin too. That means that it has geodesics that emanate, they don't intersect. These geodesics, they go all the way to infinity. I call that a center, and I replace that by some M. And R is the distance now in M. And I call this the hyperbolic extension M. And that's exactly what I have in here. So M has a center, and then I define the hyperbolic extension of M as being this. R is the distance to that origin there, and the example is that the hyperbolic, if you apply the hyperbolic extension HL, you get H plus L. Actually, this is a generalization of this example. And there are a few properties that I didn't mention yesterday. They're over there. These are the relevant properties. So here in the, well, let me do it here. So if this is M, and you do the hyperbolic extension here. If you choose a geodesic, one geodesic emanating from the origin, it's the whole thing here. Gamma is here, the geodesic in M. And then you multiply this by HK, gamma cross HK. Yes. This is, of course, a subset of HK cross HL, which is the hyperbolic extension M. So this lives inside here. Of course, this something like that living inside. If you put, if in here you put the induced metric from here, the cosine hyperbolic R metric in here. Now this is just a line in M. So the metric in here is going to give this just this isometry. And that kind of makes sense because the metric in here induces a metric on the line, and this is just a line, it's a geodesic, so the metric induced on the line is just a metric in R. So you have R cross this HK, but remember, these lines go like that, so at the end you get HK, and these are lines, but these lines go like this, and what you're going to get is just hyperbolic K space worked by hyperbolic 1 space, which is hyperbolic K plus 1 space. Not the
Pedro, do you mean to have an M down here instead of HL on the board? HK cross HL, is that what you mean?
Next to the right.
Oh, yes. Sorry. Yep. Yes. So I mean, M has a metric here, and things can be strange, but restricted on this line is just R, nothing. So when you apply the hyperbolic extension to this particular subset, you get just a copy of hyperbolic K plus 1 space. That's what I'm saying here in this property. Which one here? Here. Am I saying that? Oh yeah, that's the second property. Now, so this is k-dimensional. This is hk. So if in addition you choose a geodesic here in hk, so in general this is k could be greater or equal to 1, but if you choose in this hk a line, well, there's no way to picture that. You have a line here, so you get this line. That's what I call eta. You choose a line eta and use this gamma that I used before. So I have a line here now and a line here now. And what is happening to these lines are, this is eta downstairs, this is gamma on the vertical spaces. And remember, these whole planes go like that. So in particular, these lines are going to go like that. So it's not surprising that gamma or eta cross gamma is just going to be a copy of H2. So there are lots of copies of H2 here.
What if that geodesic is closed? Do you get the same?
Say it again?
If the geodesic is closed?
No, there are no closed geodesics here.
There are no?
No, passing through 0, there are no closed geodesics. That's the definition of in a center. Right? Something, I said that. Remember, M is, this is a center of M. If all these geodesics is go to infinity, that gives you the exponential map.
Yeah.
Just go to infinity. Anyway, so that's the second property. The third property is that you iterate the hyperbolic extension process. You just get again the hyperbolic extension of something. So in some sense it's additive, and of course that's not surprising. It's true in the case of hyperbolic spaces. If you take hyperbolic extension of HL, this is HK plus L. If you do it again, just put here, and if you do it again, then you get hyperbolic L of HK plus N, which, using the same argument, is hyperbolic K plus L of N, which is
Right, K plus.
yeah, but let me just like and the same happens. The same happens if you just put M. And the reason this works is that it's hyperbolic trigonometry. You have the law of sines for right hyperbolic triangles. If this is S, this is T, and this is and this is say this is A, then the cosine hyperbolic S is equal to cosine hyperbolic T times cosine hyperbolic A. Hyperbolic law of cosines for right angle, for right. That's true. So you use this property to prove this, because in the iteration you are going to get one, the iteration on the other, and in the working function. Well, I don't. The other property is that so this is M, and you apply the hyperbolic extension of that, then any point in here is going to be a center of the whole thing. So if you could take all the geodesics that emanate from here, they all go to infinity, they all intersect, and actually the exponential map, which is given by these geodesics, is a different vortex. So all these points are centers, and this follows from the second property, right? Because if you choose a geodesic here, there is a copy of H2 inside. So when you just shoot a geodesic emanating from here, you just go to infinity, because it's like being in H2 and just shooting a geodesic. So that way it cannot intersect with another one. So you just play with that property, and it gets you that all these points are centered. So this new thing has centers too, so we can iterate in these things. In the last property, I will make it more specific in a moment, but it says that if M is, in some sense that I explain later, is close to be a hyperbolic metric, then this whole thing is also going to be close to a hyperbolic metric, provided we are far away from HK, from this region. I will give you a more specific statement of that result later. Okay, so that's all about hyperbolic extensions. Let me discuss another geometric process. And this geometric process, I call it the two-variable warping trick. It's based on a warping trick developed by Farley and Jones. So let me first explain that. The Farley-Jones warping trick. So, first of all, remember that if you have the round metric on the sphere, and then you work that by hyperbolic sine t. Right, so this is a metric on Sn cross 0 infinity, which is Rs of 1 minus 0. And actually this gives you the hyperbolic, the round sphere, and this gives you, this metric is, this space gives you the hyperbolic metric. Right, so the metric, so if this has radius t, then the metric in this in Sn cross t is just a round metric multiplied by hyperbolic sine. Right, so the metric on the sphere of radius t is just the round metric multiplied by sine hyperbolic. That gives you the hyperbolic metric in Rn, and this extends to the whole space of Rn. Anyway, so for example, a way to think about this thing is that suppose you have a curve here on this sphere, and then the length of this curve is just the length of the corresponding curve if you put the sphere of radius 1 here, and then you just project along the rays. So you have a curve here, just a copy of that one, but with a smaller radius. So the length of this is equal to the length of this in the radius 1 sphere multiplied by sine. So everything, all distances, everything, all lengths get multiplied by this number. Right, so you have some curve here, and the length of that the length of this is just the length of that on the round sphere multiplied by sine. I'm going to use this geometric argument later, so that's what I'm doing now. Right, so everything you get just scale. The bigger the t, the bigger this number is. Anyway, so suppose now we have a metric like that one, but instead of the round sphere, we have something else. It's a metric G. So what I'm doing now is just keeping the working function, but changing this metric. Right, so now the argument is the same. You have the length of something here. The length of something here is going to be the length, but now it's not the length on the G. On the round sphere is the G length. It's the G length on the sphere. So G is a metric on Sn. Of course, if this is just the round metric, then we're back to hyperbolic. So this is given, and now as t goes to 0, this number goes to 0. So we have also that these spheres, as t goes to 0, they get smaller and smaller. So it gives you a metric again in Rn minus 0, and in general you are going to have a singularity here. You have no description of the metric at this point. You have a description of the metric around it, but in general you have no description of the metric here. If, as I repeat, if the metric was just the round metric, then this would give, you could extend everything over there and you will just get hyperbolic metric all over there. But in general you have a singularity that depends, how bad the singularity is how bad, depends on how bad G is. So if you would like to get rid of that singularity, what you will do is you would like to deform this G to the round metric. So G is here, but then you would like to change the metric and make it here, that G to make it round, and then once you have round metric near the origin, you will have something like this, which is just hyperbolic metric, and then the singularity goes away. Now, in the case of Farrell and Jones warping trick, they want to deform this to the round metric for other reasons, not for singularity reasons. They have used this deforming of G many times in this. So it looks like a very simple trick, but it's extremely useful. Being used, for they introduced this trick in 89, and people have used that trick, many times. I have used it many times. It's a very powerful trick, and even though here we are trying to use it to smooth the similarity, they do it for other reasons, for finding examples of exotic things and so on. Anyway, let me explain a little bit more how you do that in more detail. So, from now on, rho is going to be a smooth function. Just draw the picture. That is 0, the canonical bump function is 0. Before 0 is 1, after 1, and is smooth and between 0 and 1. Right, that's fixed from now on. And now we define the left alpha is some positive number. I just rescale rho, and rho of t is the definition rho of t over alpha minus 1. So what it does is alpha is 2 alpha. What this thing does is 0 at alpha, from alpha to 2 alpha goes to 1, and then it's 1. So after 2 alpha is 1, before alpha is 0. I'm just rescaling this, stretching this function, moving this, translating, and stretching this function. So that's alpha and 2 alpha. And now I define G alpha as being, I just deform by a complex combination G to the round metric. So put 1 minus rho alpha T round metric plus rho alpha metric G. Right, so I'm just taking the complex combination between these two. So in general, you will put like 1 minus T, like a segment. But you want everything to be smooth, so you have to smooth everything out, so you use the bump function instead of T. Anyway, so this is just a complex combination. So this metric is what? This metric is when T is less than alpha, the rho is 0, so that's 0. So when T is less than alpha, you just get the round metric. And when T is bigger than 2 alpha, you just get G, this goes away. So T is bigger than 2 alpha. So now you have G here. So you can think of G as being exchanging. G alpha exchanges here is, this is alpha, this is 2 alpha. So here is just a round metric, and here is just G, 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 and here is just a round metric, and here is changing. And now I want to smooth. I want to smooth this metric to like the 0. Remember, so what I do is I define H alpha by the same formula, but instead of putting G, I put G alpha. And this has the property that when T is less than alpha, this is just a round metric, right? So when T is less than alpha, this is just sine hyperbolic T square round metric, which is just a nice hyperbolic metric. And for T bigger than 2 alpha is hyperbolic with G, which is H. This one. So I didn't change anything outside the ball of radius 2 alpha. Inside the ball of radius alpha, now I have the nice metric. It's just a linear combination. I have, it's nothing really difficult. It's just, just a complex combination of things. So I changed outside. I didn't change anything outside, and inside I just have the round metric. But the important thing here is that theorem says that sectional curvature. Now, the K, I'm using this notation. These are this means sectional curvatures of this metric. It's a short notation. These sectional curvatures tend to -1 uniformly as alpha tends to infinity. So this simple change gets you metrics that get sectional curvatures as close as -1 as you want, provided alpha is very big. I mean, that's not surprising in the ball of radius alpha, because in the ball of radius alpha, you actually have hyperbolic metric, which is the sectional curvature of -1. So that's not surprising. But the most surprising thing is that between alpha and 2 alpha, when the thing is changing, you get metrics whose sectional curvatures are close as -1 as you want. Now, I'm going to give you an idea why this is true. And the idea would be to apply Bishop O'Neill's.
So is this some kind of uniform? Is that what you mean?
Yes, uniform.
Okay.
Yeah, so all sectional curvatures, because this is a metric defined on sphere cross zero infinity, and all of them, so if alpha is, so if you say I want this to be close to 0.001 close to -1, then if I take alpha bigger than 1,000,000, then all the sectional curvatures in every point, all the way to infinity, all of them are close to -1. So remember Bishop O'Neill's formula for the sectional curvatures of a warp bar. Lambda squared plus sectional curvatures of the section. F prime square over F square and B square. The important point here is that lambda square plus B square is 1. So this is a formula to finding the sectional curvatures of a word product. Problem. This H alpha is not a word method because this is changing with G. I mean, that's actually the whole point. You have to change. You are changing it, right? So this is not. If this was fixed, it was G, then I can use this formula. But it's changing, so I cannot use that formula. So, I will probably have to sit down and compute all the compute the sectional curvatures by hand. Find a new formula for this type of things. and actually that can be done. And I do that in the paper, but apparently just they don't do that. They use a direct approach. But I can explain why this happens. And the reason is the following. Remember this alpha. This alpha is a function that is 0 here, the reparameterization of the function. And then it goes from 0 to 1, and then it's 1, right? So the G alphas are round here, up to here, they are round, and then they change to G from here to here, and then it's G all the time. So you are changing the round metric to G in the interval alpha to alpha. Now if alpha is very, very big, this change is going to be very slow, right? So if t is time and alpha is like 1 billion, so it will take 1 billion years to change from this to that. So if you stand here and you just measure one time with your clock and say, well, let's see if the metric is changing. And in 1 minute you will say, well, it's not changing. It looks constant to me. It has to happen in a billion years. In 1 minute, nothing happens. So the metric is not constant, but if alpha is very big, it's going to look like a constant. So the sectional curvatures of G alpha, of H alpha, are not equal to this because that metric is not work. But if alpha is very big, what I can do is kind of say they're close to. That makes sense. So and this approximation gets better and better as alpha gets to infinity. Because if alpha is bigger, then the change happens even slower. So I'm not proving anything. It's just kind of. So if I put f is hyperbolic sine, so hyperbolic sine. So that's minus lambda squared plus the metric of G alpha, whatever they are. This is sine hyperbolic squared t, cosine hyperbolic sine cosine hyperbolic squared t, d squared. Now I add and subtract 1, so this is plus 1 minus 1, so you get 1 minus cosine hyperbolic squared t over sine hyperbolic squared t, b squared, but I added, so I get minus plus kg minus 1 over sine hyperbolic squared v squared. I have just added plus and minus separated into pieces. This is again minus 1, so you get minus lambda squared minus v squared, which is minus 1, plus this part here, which is minus 1 plus kg alpha minus 1 over sine hyperbolic squared. This depends on g and the round metric. Right? So this whole thing is a constant. So this is of the order of minus 1 plus some constant e to the minus t, because this is the order of e to the minus t, e to the t, so some number here that is bound. So as t gets bigger and bigger, this thing gets smaller and smaller. So if this number is big, this gets very small. So we have two approximations here. First, this is not equal, it's close to being. And the bigger the alpha, that's lower the bigger this number, that's lower the change, so the better this approximation is. And there is also something here. You have an error, this error, and this gets smaller and smaller the farthest you are from 0. If t, because here nothing happens because it's round. It's a round metric, so everything is that error there is 0. But after here, you're going to get some things that are not 0. But you can make that small provided alpha is big. This alpha. So you want this alpha to be big for the approximation, and you want this alpha to be big so that this is. Happens that here the alpha is the same. And so what I needed was actually it's the same trick, but with a bit more freedom. I wanted this distance to be independent from this distance. So I call this a B and this is A, and I just do the same thing, and I have two different variables, and I call this the two-variable working trick. Actually, that's kind of a new name because I used to call it hyperbolic forcing. I don't know why, but I changed that to two. So if you read the big paper, it appears. I used to call that hyperbolic forcing. So now it's called. It's decided to change the name. Two-variable working. So now this is what I just said. Harlan-Jones, here it is. This is what I just mentioned, G alpha, H alpha, and this is Harlan-Jones theorem, and this is what I just wrote it over there. And now this is a two-variable working trait. Now I choose two numbers, A and D, and define rho AD. Now remember, this is worked by rho alpha, right? Rho alpha is 0, 1, 0, 1 here, and between 0 and 1 here. Now I'm going to define rho AD of t as being rho, the bound function, what is that? A, t minus a over d. This function is 0 up to a, goes a plus d, and then is 1. So this length is d, this length is a. So it's the same thing here, but in here a and d are equal. Well, actually I put the 2 there, so it's really d over 2, but that's a technical reason. So don't worry about that. Anyway, so now I just do everything, but I replace alpha by rho AD. And so now I put AD, and in the definition that I read, anyway, it's over there. No, yes, it's over there, rho AD. I just put, instead of rho alpha, I put rho AD. Everything in there. And same thing as before. alpha AD, then for t less than a is the sigma, the hyperbolic one. For t bigger than a, b plus 2 one is h. And then have this theorem here. And this theorem has a few new features. It's more specific than the Farrell-Jones theorem over there. Here it says that if alpha goes to infinity, then the sectional curvatures get close to -1. This one says, it's more specific, I needed something more specific. It says essentially that if A and D are very big, this is very small. Right? This is a constant that depends on n and c. C is a C2 norm of G. So you take G, you fix some atlas, and then G is a metric on the sphere, and then you just C is the upper bound of all partial derivatives up to order 2 of the metric. You just represent the metric by matrices, there are functions, and you just take the C2 norm of that. Right, so if G is very bad, that C, G kind of changes really badly, then this C is big. But it depends, this C depends on G. Right, so it will be very big depending on C. But once G is fixed, this is fixed, this constant is fixed. So if you take A and B very big, this is going to be very small, and the metric HAD is going to be epsilon close to hyperbolic. So this is more specific than saying that the sectional curvatures are close to -1. I'm going to explain you what epsilon close to hyperbolic means. So in particular, if the metric is epsilon close to hyperbolic, then the sectional curvatures are going to be close to -1. A metric being epsilon close to hyperbolic means that the metric is close to hyperbolic by charts. So this is the definition that I'm going to give you in a moment. But let me just say that what we do is this. We fix a model, say like a ball in hyperbolic space, some radius is fixed. And we say that some metric is close to being hyperbolic with respect to this model if every point has a chart such that the pullback of the metric in the space. So you pull back that, you get something in the model, and then you compare the metric in the model with the metric that you just pulled back, and you want them to be close. So it's a chart-by-chart definition of that concept. Here is the definition. So, I mean, the reason I had to do that is because sectional curvatures being close to -1 is not powerful enough. I mean, I don't know. At least I don't know how to make to preserve that property using all the tricks that I use in here. For example, a hyperbolic extension. If the metrics are close to -1 in here, is it true that once I do the hyperbolic extension, the metrics are close to -1 in the hyperbolic extension of it? I don't know. It's probably true, but the proof looks very, very, very hard to do. There are lots of calculations. But if instead of assuming that the metrics are close to -1, I assume something stronger, that the metric is actually close, looks like being hyperbolic. Then that is nice with, that is easier to prove that, it is easier to prove that then when you apply the hyperbolic extension, then the whole thing is also going to be close to hyperbolic. Maybe not that close, because that epsilon will change, but you can work with that. And all these tricks that I do, all of them are, these properties preserved nicely. So this one is not that nice to work with, and I spent a long time trying to do that. Then I changed this property for that one. That's much better. It's more stronger, but it works. And here is the definition of epsilon hyperbolic metrics. There is a model here. The model is you just fix a ball. This is a ball in Rn, and multiply that by an interval of length depending on that psi over there, and then you just warp. So here you put a flat metric, and then you warp this by exponential t. This, when you compute the metric of the sectional curvatures, that the sectional curvatures are all equal to -1 using this formula here. And so this is a fixed model in hyperbolic space. This is a subset of hyperbolic space. And then I say that something is epsilon close to hyperbolic. A metric on a manifold is epsilon close to hyperbolic. If every point has a shard, has a hyperbolic shard, that means epsilon hyperbolic shard. That means for every point there is a shard, so that you pull back the metric, you compare the pullback metric with the metric in the model, the exponential one, and they are close. So this metric in this chart looks very, very much like this one, up to epsilon. So that's what I said, that a metric that close to hyperbolic is the metric in a chart looks close to being, the canonical one in the model. And that if I want to, I mean, this is a too much about that, but I'll explain it anyway. So here, this is a product. Remember, I'm taking the whole cross lines, so I have lines here. Because I'm multiplying here by an interval. And suppose you have an m here, and suppose the metric is warped. And this is an interval again. Dealing in lots of metrics. These are all warped, so they have lines too. So this is a more specific, stronger definition. A metric is warped epsilon hyperbolic if the charts that I have, remember, the charts at every point has a neighborhood, and a chart that maps this to that such that when I put the metric here, that metric is close to the canonical one. If that chart preserves the lines, sends these lines to these lines, then I say it is warped epsilon close to hyperbolic. It looks technical, but that's what happens in here, that's what appears. Anyway, just a technical point that really.
Why are we putting the flat metric on the ball?
Well, this is a subset, a metric subset of hyperbolic space. The sectional curvatures are -1. If this is flat and I am warping this by exponential t,
Okay.
this is hyperbolic. And the reason really why I'm using this is because, remember if you take a metric on the sphere and you warp this by sine hyperbolic squared, and you make t very, very big. So the matrix on the sphere, this is just the metric, any metric on the sphere multiplied by sine hyperbolic tg. So it's just any metric on the sphere multiplied by this big number. So this is a big, huge, it doesn't matter what this is. If this is big, this is going to look like a flat space. Right? So if you take any Riemannian manifold and multiply it by a huge number, locally this begins to look like, you have a sphere and you make it really, 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 really big, it looks like flatter and flatter. Right? So the metric in here is going to be closer to something like this, like Euclidean, but you are working by hyperbolic sign. So, and a hyperbolic sign is pretty much like exponential, 1/2, some function, doesn't matter. So locally, this thing here is going to begin to look like this. So that's the model. In all of them, that's the kind of the easiest one. So these things resemble that for TB. So that's the real reason I chose that model. It was just to simplify, I have to choose one. Any one that I chose would give me kind of error, and I just chose that. Anyway, so that's the definition of epsilon property. It's a kind of a technical thing, but let me add one thing about epsilon close to hyperbolic metrics. Is this one? If you have a metric, if you have a manifold that is work epsilon hyperbolic. It has a center again, and this is what I said. You have here a manifold with a center. Suppose this one has a metric that is epsilon close to hyperbolic, and then you apply the hyperbolic extension of that. And it happens that away from the wall of radius r, the resulting metric is eta close to hyperbolic. And eta can be taken in terms of epsilon and r. So if you want eta to be small, you want, of course, epsilon to be small, and you want to be really far away from r. So if you have here a manifold with a center, and suppose you know this is epsilon close to hyperbolic, or even what epsilon close to hyperbolic, and then you apply the hyperbolic extension, and if you are far away from this section here, this is hk, so you have to be up here or down here. In here, the metric is eta close to hyperbolic. And the exact amount is given by that formula. Right. The farther you are away, the smaller this number is. This is the epsilon that comes from m. So that's cool. But you need more specific formulas for the whole thing to work. Okay, so I explained epsilon hyperbolic metrics. What do I have here? Oh, dimension 2. So now let me explain a few elements here. So now I can explain how to smooth metrics in dimension 2. So what I'll do is explain dimension 2, explain dimension 3, probably tomorrow. And maybe see a little bit how to extend that to higher dimensions. So, remember the hyperbolization process is done in this way. We have the canonical cube. Remember, this is just a canonical cube. This is 0, 1, or 0, 1 k times. Above it, we have in HQ. This is a hyperbolic manifold, compact hyperbolic manifold with boundaries. And with boundary, I use the notation P inverse of any subcube. If you have a subcube here, I will call that X. Yeah. So and these are, as I said, this is a hyperbolic manifold with boundary, compact, it has corners, and in dimension 2 you can think of the square here. And well, I mean, rigorously I should draw something with higher G whatever. Anyway, and so if you have a subcube like this one, the pre-image is something here. In dimension 2 it's going to be a segment too, but in general it's going to be something else. So this is a hyperbolic manifold, and the important thing here is that, of course, this is a square, so these are 90 degrees, and these two are perpendicular. So in general, the pre-image of something is totally geodesic in here. So this pre-image of this segment is totally geodesic here. The pre-image of this segment is totally geodesic here. And these two things intersect perpendicular. So these are also 90 degrees. And so now suppose you have a cube complex, and then you replace every cube. You replace every cube in K by the hyperbolization of this, and you obtain what we call it the Shawnee-Davis hyperbolization of K. We call it X. So in the simplest case, like I have over there, if you glue if you glue 4 squares, what you get is a big square. You just glue these things, you get a big square. And metrically too, if you just identify these metrically, you just get something like that. But if you, instead of gluing 4 pieces, you glue more pieces. Oh, and before that, I mean, if you do that in here, like over there, and you glue 4 pieces here, with the 4 pieces, you get a picture over there. Now, as I said, this is a hyperbolic manifold. So near here, this region looks like a quadrant of hyperbolic space. So this is hyperbolic. If you think the disk model, hyperbolic space, this is two geodesics that intersect perpendicularly. This is a quadrant hyperbolic space. And in particular, if you take a radius t here and measure, remember the length of this whole thing here, the length of this circle is 2 pi, which is the length in the Euclidean case, t is 1, and then you put sine hyperbolic. So that's the length in hyperbolic 2 space of a circle of radius t. Remember, because it's 4. But if you take just one quadrant, then the length of this little piece is that divided by 4. Right, so this is 2 pi sine hyperbolic t divided by 4, 2 pi divided by 4 divided by 4 here. And at the end, when you do everything, you got that picture and you have a little circle. In other words, I mean, if you have 4 squares and you do it in here, you are just doing a quadrant of hyperbolic space, a quadrant of hyperbolic space. This is just hyperbolic space, hyperbolic metric. There is nothing there, no singularity. Just 4 pieces of hyperbolic space. But, so this is the easiest example. This is the only one that is actually works. What if you don't have 4 pieces and you have the, like my Pedro model down here? So instead of having this, you have that thing down here. And you do it up there. Then the metric in here, if you take, we have the property that if you take a radius t and measure the length of the circle, you have 6 of these. So in that case, the length of each circle here, as I said, is this, and you have L of those, 6 in this case. Then the length of the circle, right? So instead of having that, you have more. 1, 2, 3, 4, 5, and 6, and then you do the hyperbolization here. 1, 2, 3, 4, 5, 6. And the length of this thing here is 2 pi sine hyperbolic t divided by 4, but you have 6 of those. Yeah, let's suppose you have L of those. So let V be contained in L squares, two squares. Then the metric near here, because the length of this thing here is going to be 2 pi sine hyperbolic 2 pi L sine hyperbolic t over 4. Right, so then the metric is going to be then the metric near V in the hyperbolization is L over 4 hyperbolic sine square t. the round metric on S1 plus dt squared. Let's call this sigma L. Because this gives you the length. In particular, if L is equal to 4, L is equal to 4, that's 1, and that's just a hyperbolic metric. If L is different from 4, you get a different number. And the fact that you have a singularity is seen here. If this number is not 1, then you have a singularity. So, in other words, you know, if I replace this example with this example, I get a description, an analytic description of the metric around that singularity, not in the singularity, but around it, by a nice formula over there. And if that number L was, as I said before, was 4, then I wouldn't have a singularity. But if L is different from 4, I have a singularity. And so this is valid around the singular point. And I want to smooth that out. We make the metric nice and smooth near the vertex. So I want to deform, I want to change that number by 4. So in general it's L, in general it's in any number L, if you want it to be 4. So you just do the trick. You begin with L, apply the rho alpha. It's going to be L, then it's going to change from L to 4. Or in other words, this number becomes 1. And then for less than alpha, less than A or B, whatever, it's going to end up being 1. So it's going to be near the singularity is going to be a hyperbolic metric, and then there is no singularity. So you define GL as being 1 minus rho AD. I'm going to change the R. For notational reasons, I'm going to write R as A plus B. So R minus this A. So this is AD. This is the AD before it's just changing the number P. And I want this number to be, so I want it to be 1 plus, so maybe define eta RV of T as being this number plus rho R minus B of T times L. So this is just a function that is what I'm doing here. This is R. This is R minus D. This function is 1 here. This is 1, and then eventually goes to L over 4. So for T bigger than R, this is just L over 4. The function eta is just L over 4. And for T less than R minus D, the function eta is 1. And I'm going to put eta here. Right, so T is small, this becomes 1. T is large, this is L over 4, which is the open. So now, now I define GL as being eta T squared sine. Oh, I think I made a mistake here. Should have been squared because everything is squared. So yeah, so sine squared T minus 1. I'm just changing this. So this number for T small, this is 1. For T large, this is L over 4. So this GL. So GL is equal to the round metric, to the hyperbolic metric, for t less than r minus d, and if the old one is my for t bigger than r. Right. So
upstairs, that should be that's A to the subgroups or am I
which one?
right up there, that, or is it, am I missing something?
This is probably r minus subgroup. So originally we had a singularity here. This near the this point we have a singularity here. So what we are doing is just changing the metric. Here is the same. I didn't change anything. In here I make it hyperbolic, and this singularity goes away. That's what I'm saying. That's what I'm doing. It's not really. And this looks like a. I put the square over there. Exactly what I wrote over there. And now, I change everything. This is the new metric here. Outside, I didn't change anything. It was but I didn't have a problem there. The problem was in here, so I just changed it in here. And this is pretty much like the part that you know is working tree. And I mean, it's not hard to prove that if R and D are very large, using the same argument I used before, if R and D are very large, this happens very slowly, all that stuff. The circular curvatures of this metric are going to be close to minus 1. Here is they are equal to minus 1. And if R and D are very large, this is the metric of the whole thing is going to be close to minus 1. So that's how you smooth out in dimension 2. It's pretty simple. And so my time is up. So tomorrow I will try to explain how to do it in dimension 3, and hopefully a few more things.
You sort of emphasize the case where you have more than 4 squares, but this looks like this works even if you have three squares.
Yes,
So you don't need any non-positive curvature out of the trash.
So this can go down to, as long as you have big space to do this stuff. If you don't have big space, then you cannot do it. So if that's kind of an open problem, then probably it could be done. If you assume the lengths to be large, then probably it may be possible to smooth the metric still there and make it negative curve, but not close to minus 1. Couldn't be. Right, like with this Gromov-Bergman example. I mean, they made these things really, really big, and then you need huge space to smooth. If you don't have that space, you cannot smooth. Make it close to minus 1. But you can still
So is that Pedro again?